This module will talk about partial correlations. Partial correlations are used when a researcher may wish to have a measure of strength of relationship of the linear interdependence between two variables when the effect of the remaining variables has been removed. Or their alternative term we use are whether the effect is kept constant or it is being controlled. So such a measure is provided by the partial correlation coefficient. The partial correlation coefficient may be computed from the simple correlation coefficients. Suppose we have three variables, y, x1, and x2. The sample partial correlation coefficient measuring the correlation between y and x1 after controlling for x2 is denoted by r y1.2. This expression shows that r is for the coefficient of correlation, y is for variable number 1, and 1 represents x1, a second variable. So here we are interested in looking at the correlation between y and x1, hence we have written r y1. Whatever goes after dot, in this case it is dot 2, which represents x2. This effect will be held constant or being removed. So in the subscript, the symbol on the right of the decimal indicates the variable whose effect is being controlled. So for the three variable case, there are two other sample partial correlation coefficients that we may compute. There are ry2.1 and r12.y. So ry1, which is a simple correlation between variable y and x1, ry2, which is the simple correlation between variable y and x2, and r12, which is the simple correlation between variables x1 and x2, is calculated. And these values are used in the formulas to calculate partial correlation coefficients. The sample partial correlation coefficient that may be computed from the simple correlation coefficients in the case of three variables are given by ry1.2, ry2.1, and r12.y. Here, if our interest is to look at the partial correlation between variable y and variable x1 after controlling for the effect of x2, we'll write it as ry1.2, which is equal to ry1 minus ry2 multiplied by r12. Whole thing divided by the square root of the 1 minus ry2 square and 1 minus r12 square, the product of these two terms. Likewise, we can calculate the partial correlation between y and x2 controlling for the effect of x1 and x1 and x2 controlling for the effect of y. Let's take an example where Wong et al. Using cadaveric human femurs from subjects ages 16 to 19 years. They investigated toughness, properties of bone, and measures of the collagen network within the bone. Two variables measuring the collagen network are porosity, that is P expressed as percentage, and a measure of collagen network tensile strength, which is denoted as S, and the measure of toughness, which is denoted by W, and it's measured in newtons, is a force required for bone fracture. So the 29 cadaveric femurs used in the study were free from bone-related pathologies. We wish to analyze the nature and strength of relationship among the three variables. Data is given in the table on the right, and we are using this information to calculate, firstly, the Pearson's product moment correlation coefficient, assuming that all the other assumptions are being fulfilled. We use the formula for the Pearson correlation coefficient for all three pairs of variables. So if we calculate RWP, it is 0.043, which is a very small correlation, which represents a very weak amount of relationship. Then RWS equals 0.535, which is relatively stronger relationship between the variables, and RPS, which is minus 0.080. This shows a negative sign, which shows that there is an inverse relationship between porosity and strength. Though this value is very small, but it still shows that there is some relationship that exists there. All these three relationships are measured using Pearson's product moment correlation. And we understand that Pearson's product moment correlation coefficient gives us the linear interdependence between these variables. All three measures represents the linear interdependence between these variables. So using these simple correlations obtained as RWP, RWS, and RPS, using the formulas for the partial correlation coefficient and measuring the correlation between toughness and porosity after controlling for the effect of tensile strength, we include these simple correlation coefficients into this formula and we get the value to be 0.102. One might notice that the correlation between RWP is 0.043. But if we control for the effect of the tensile strength S, the correlation has gone up and this is 0.102. So this clearly shows that there was some effect of tensile strength on the relationship between toughness and porosity. We can, vaguely say that there is this increase in the relationship, so there was a significant impact, but for this, there are some inferential measures that need to perform. But this certainly gives us a very good indication that tensile strength had some effect on the relationship between W and P. Likewise, calculating the partial correlation between toughness and tensile strength, controlling for the effect of porosity, we get it from RWS.P. So using the values from the simple correlation coefficients obtained, RWS.P equals 0.541, which is almost the same as RWS, which is 0.535. A very slight difference. So one can see that porosity might have some very little impact on the toughness and tensile strength here. But certainly, again, it has to have some inferential analysis being performed to make it sure that how much effect is out there. But this correlation tells us that toughness and tensile strength are related to each other by 54.1% when the effect of the porosity was held constant. Thirdly, the partial correlation between tensile strength and porosity after controlling for the effect of toughness is obtained as RPS.W, and this value is minus 0.122 when the original value was RPS equals minus 0.080. Again, there's a change in the value which reflects that toughness had some impact on the correlation, but when you control for this effect of the toughness, the correlation coefficient between tensile strength and porosity goes up, which shows that if there is negative relationship between porosity and tensile strength, and there is 12.2% related. We'll perform the same example using SPSS. Here we have all three variables included here, where W represents toughness, P represents porosity, and S represents tensile strength. To calculate the partial correlation coefficients directly, we'll go to the correlate and partial, and we bring the variables one by one. So if we are interested in calculating the correlation between toughness and porosity and controlling for the effect of the tensile strength, we'll bring those variables here. Since our interest is to look for this relationship, so we'll do the two-tailed test and press OK. A table is obtained, that is a 2x2 table, which shows that the toughness and porosity, the amount of correlation is 0.102 when we controlled for the effect of tensile strength. Likewise, if we want to look at the relationship between tensile strength and toughness, controlling for the porosity, we change the variables accordingly and simply press OK. This is going to give us the correlation coefficient between toughness and tensile strength, that is 0.541, controlling for the effect of porosity. And likewise, for the third case, where we want to look at the relationship between porosity and tensile strength and controlling for toughness, the value is minus 0.122. So this is how we measure the partial correlation coefficients using the software. Thank you.